In this video, we'll be covering section 8.2, slope fields and Euler's method. We have three objectives. The first one is to draw slope fields for a given differential equation that has this particular form. Then we will use slope fields to help us sketch a solution curve that goes through a given point. And then finally, we will apply Euler's method to approximate the solution to a differential equation. So what do we mean by slope fields? Well, if we think about the types of differential equations that we solved in the previous section, they were the most simple type. They all had the form of this. The derivative was just equal to some function of x. So maybe it was, dy dx equals 3x squared minus 1. And the way we would solve this differential equation was simply to take the antiderivative on both sides. Well, in this section, our differential equations are going to be more complicated, and unfortunately, they just can't be solved like this. So the difference is, instead of just having a function of x on the right-hand side, we may have x and y on the right-hand side. So this over here would be a good example of that type of differential equation. We have the derivative is equal to the function times the quantity of the function minus 2 times x. So a much more complicated expression. We can't simply solve this by integrating both sides, because this would need to be integrated with respect to x, and there's no way to do that with a y here, because y is actually a function of x. Okay, so the best thing we're going to be able to do right now is just to get a picture to help us approximate the solution. And this is where slope fields come in. So if we actually analyze what this is saying, this is saying the derivative equals this expression. But if you remember, derivative is slope of a tangent. So the idea is this equation is giving us a formula for the slope of the tangent at any point in the coordinate plane. And notice it's at any point xy, meaning every single point in the plane we can find the slope of a tangent. So a slope field is the process of just doing that, taking every point, or really just a finite subset of points in the plane, and plugging them into this expression. So what do I mean by that? Well, I've already made the slope field for this differential equation here, so let's just take a closer look at one of the points, and we're going to look at the point 1, 1. So that's when obviously x equals 1 and when y equals 1. Well, according to the differential equation, dy dx, when evaluated at the point 1, 1, this is the way it's typically written, take the derivative and plug in 1, 1, meaning plug in 1 for x and 1 for y. That would be 1 times 1 minus 2 times 1. And then we simplify this, so that's 1 times negative 1, which comes out to negative 1. So the way to interpret this is, if the solution to our differential equation goes through the point 1, 1, then at that point the tangent should have a slope of negative 1. So let's go to the point 1, 1. Here's 1 for the x, here's 1 for the y, and look right there at that point we've drawn a little tangent line, and you can see that it has a slope of negative 1. So if the solution, this is kind of showing you the flow of the solution, if it were to pass through that point, it would have to have a slope there of negative 1. This could be a rough approximation of that particular solution. Right? The way to interpret this is it's kind of giving you the flow of all the different solutions of this differential equation. Let's try a different point just to make sure we're clear on what this is actually saying. So let's pick the point, let's do 1, 2. So we're going to evaluate the derivative, dy dx, at the point 1, 2. So plugging everything into that, 1 times, oops, sorry, I got that backwards. All right, plug in 2 for the y, so 2, and I don't need that parenthesis. All right, 2 times 2 minus 2 times 1. All right, I think we got it right that time. And then simplify this. Inside you can see that's just 2 times 0, so you get 0. So we're saying the slope of the tangent at the point 1, 2 should be 0. In other words, we should have a horizontal tangent. Well, let's go to that point. 1, go up to 2, and you can see at that point right there, you do have a horizontal tangent. So if we were to have a solution passing through this point, well, it's going to be different than the blue one, but it's still going to kind of follow the flow of all of these little segments. So it might look roughly like that. Remember, a given differential equation has infinitely many solutions. In order to get one of these solutions, you would need an initial condition. So the green one could have the initial condition that when you plug in 1, you get out 2. Right? If we include that initial condition, then this might be the graph, or a rough approximation of the graph of the solution for that particular initial condition. All right, let's see this in motion. I have a little construction that actually will interactively show you all the solutions. Okay, this is the same slope field that you have seen on the other slide. All I've done is suppress the individual points, all those lattice points, so you just see the segments themselves, but it's the same thing. So the idea is, suppose we start with some initial condition, meaning some point. We want our solution, let's put it over here on the y-axis. We want our solution to go through that point. Then the curve has to follow these little tangent segments. So let's actually turn the solution on. It should look something like that. You can see the blue line there is following all those tangent segments. And if I move this point, it continues to follow the flow of the slope field. So we get each of those individual solutions. Right, these give you some nasty ones with vertical asymptotes, but no matter where I put that, it follows the slope field. So this is what they do for us. They give us a visualization for all of the different possible solutions for that given differential equation. Okay, so let's try making one for ourselves. The process is simple, but it is tedious because we have all these different numbers to plug in. Now, I have updated the notes. I'm going to try to include a PDF version of the updated notes. Basically, what I did is I reversed the order on this column here for the table, and I did that so that the actual elements in this table would match up with the array of dots that you see here. So notice the order here is matching the order of the y-axis. So in your notes, I think I just have this column reversed. Okay, so what we need to do is we've got a differential equation here, dy dx equals 1 over x squared plus 1. So we just have to take the different lattice points, and these would just be predetermined. You'll be told how many different lattice points to make here, and you plug the coordinates for those points into this expression. So the first point is really the point -2, +2, right? It's referring to this point right here. So we want to take those coordinates and plug them into this expression. So we're going to try to do most of this in our head so I don't have to write it all out. If I put in, notice there is no place to put in the y, so I only have to put the x in on this one. It just makes it a little bit nicer. So if we put -2 into the square, it's going to wipe out the negative and add the 1 to it, and we should get 1/5. Now, as I mentioned, there is no y in this expression, which means that this entire column is going to be 1/5. It doesn't matter what the y value is. The x value completely determines the slope. That's not always the case. It wasn't the case in the previous example, but it is in this one. So all of these columns, or each individual column is going to have the same number all the way down. So that first one is all 1/5. Okay, the second one, we plug in the -1. Technically, we should be plugging in both numbers, the -1 and the 2 for the y, but there is no place to put in the -2. Okay, so put -1 in and simplify, you get 1/2. And just as the previous column, it's going to be 1/2 all the way down. Next column, put 0 in, you get 1 all the way down again. Plug in 1, and you're going to get the same thing as this over here. It's going to be 1/2 again. And then plug in 2, and again, you're going to get 1/5 again. So a lot of symmetry in this array. They're unfortunately not all going to be that simple. Okay, so we have all the different slopes. Now we just need to draw them. So let me get out a straight edge if you do have to do these by hand, you are definitely going to want to use a straight edge to draw them. This is something that is very common on the AP test, and even though they've shortened the AP test this year, this is still listed as a topic. So and usually, you know, that when they have one of these, it'll be a smaller array than this, maybe like a 3x4 array of dots, but they typically do have you draw in the slope field. Okay, so normally we would start with the point right here. However, I'm actually going to start, switch over to my mouse, I'm going to start with the point right here, just because it'll be easier to get it started. So the slope of 1/5 means I need to go up 1 over 5 units, but I'm actually missing the dot for that, so I'm just going to put one in as a placeholder here. It'd be roughly about there. Okay, so then I can take my straight edge, align it with this point here, and I'm going to rotate it. Actually, I'm going to need to extend it a little bit, and I'll rotate it up to that. So this should be up 1 over 5 units. So then, using that slope, I can come back and just put a little segment right there. Now, when you're doing these by hand, what I recommend is you just take your straight edge, and just, since this entire column was all the same, try to just slide it down without changing its slope, and then you can just draw another piece. And you can do that on each one. Just nice little short segments. And then I can go back up to the top. So all those should be parallel since they all had the same slope. Okay, so then you move on to the next column and you do the same thing. So again, I'm going to start down on this point. It's just easier to get started there. And this time we're doing a slope of 1/2. So up 1 over 2, right? The slope in this column is 1/2. So then just come back in and draw in your segments. And obviously you can now appreciate how tedious this is. And again, since the whole column has the same slope, just keeping the same setting to draw each of these. Okay, so got the first two columns. Next column is going to be done the same way. You set it to the appropriate slope, which would be a slope of 1 now, and then draw in the segments. So I'm going to pause here and fill the rest of this in just so that we don't have to waste time watching me do this slowly. Okay, so there we have it, completed slope field, and it looks okay. It doesn't really give us that much information because there's not very many grid points here, but you can see it takes a while just to get this amount graphed. So, you know, they're not that useful when you have to graph them by hand. Typically, you want to make these with hundreds of nodes in them if possible. So what would it look like if we had more segments? That gives us a much better picture. So, so they can still be hard to read, but you can kind of, you know, approximate what solutions might look like. So to do that, let's just say we pick a point on the y-axis, like I pick this point here. If I wanted to approximate a solution, I try to just kind of follow on or between these individual segments here and look at what the slopes are doing. And so what I see is as I go this direction, each of the slopes is becoming less and less steep. So I'm trying to flatten out as well, and then I can see the same thing happening back in this direction. So if this was our initial initial value, then this would be a particular solution, or at least close to a particular solution passing through that point. Okay, let's try one more of these. So again, the table over here, the Y column is reversed from what is in your notes unless you printed out the new version. Okay, so the differential equation in this case is we now have a y involved, so we're not going to be able to just use the same thing down the first column. We're going to have to be a little bit more careful with this. Okay, so if we start with the first one, the differential equation just says to add the x and y values. If we add the x and y values on this, we just get 0. Then we're going to just keep doing that. Add each of the x's and y's in each column. So that's -1, -2, -3, -4. Just adding the corresponding x and y. Then do the same thing going down the next column. So it'll be 1, 0, -1, -2, -3. We're just counting basically on each of these. All right, the next one is 2, 1, 0, -1, -2, then 3, 2, 0, oops, sorry, that's 1, 0, then -1, 4, 3, 2, 1, and 0. So notice this diagonal here is all zeros. Actually, they're all the same on the diagonals. And that will actually show up in when we go to graph these as well. All right, so let's do a couple together and then I'll finish it off screen here. Okay, so if we start with, you could actually graph this diagonal first. So that diagonal tells me that each of these grid points along this diagonal, there are horizontal tangents there. Hold on, I'm going to switch to the mouse again. So undo that, try again. Okay, so we've got each of those horizontals in. Then you could go back, if you wanted, you could graph all the ones that have a slope of 1. So that would start on this diagonal here. So I'm actually going to set my straight edge first. So slope of 1 would look like that. So I'm going to go through and put on each of these along that diagonal a slope of 1. All right, so we have each of those -1s in there. So now let's go through and put in the ones that have a slope of 2 starting here at this point. Let's readjust the straight edge to be a slope of 2. It's set to go up 1 over 2 now. So I will place it here and draw in those segments. Okay, so now we have that row on there. So then we just continue with all the other dots. Notice that down here in this region, all the slopes are going to be negative. So I'm going to go ahead and just complete this and join me back in a second here. Okay, so here we have the completed chart, completed slope field. And then just like the last one, it's not particularly clear what's happening with the slope field. There's just not enough points. So what would it look like if we had more? I think actually, oh, maybe I don't have an image of that. Hold on one second. Okay, here it is. So this is what the slope field looks like if you put more segments in there, so you get a much better picture of what's actually happening in this figure. Okay, so then it said, given the slope field, sketch the solution that has this initial value. Now, I've already done that over here, but if you were doing this on your own, you would go to that point where x is 0, the y value is 1, and then you just try to follow the direction of each of these tangents. You can see it's kind of curving up here and coming back to that line. So that's where this would have been created. If, let's just look at a different one. Suppose we would have started with this as our initial value, then it looks like the curve would have kind of just come back like this. It still would have approached, you can see this kind of diagonal line here, it would have gotten close to that. I didn't do a great job of drawing that one, but those would be other solutions with different initial conditions. Okay, so it's really tedious to draw these by hand, so that for that reason I made a computer program to help us with this. So I'm going to try somehow to find a way to send it to you guys. I may have to send directions on a different program that you can download to actually add the programs if you don't know how to do that. But let me bring up the calculator and show you how the program works. Okay, so the first thing after you get the Calc pack added to your calculator is that you'll need to unpack it. So the Calc pack is given to you as a group. So to unpack it, you go second, memory, which is the plus button, go down to option 8, and we're going to go over to ungroup. This is the same way that we've created backups in the past. So we want to choose Calc pack, and then I already have all of this installed, so that's why it's saying duplicate, and we're going to just overwrite everything that I already have. And this should include these 5 programs here. There's one for Euler's method, which we're doing at the end of the notes, Newton's method, which we did back in a previous chapter, Riemann sums as well as trapezoid sums are in this program, and then slope field and square root simplification. So this is just a little bonus one I gave you here at the end. It will simplify square roots for you. But what we want right now is slope field. So to activate it, go to Program and choose slope field. So then in the first menu, you have the choice to enter in your differential equation or use one that's already maybe entered into y1. We don't have anything entered yet, so let's go to the first option, and our dy dx is this expression here, x plus y. So we type it just like that, x plus alpha y, and then it generates the image of the slope field for you. There are some settings to tweak how long these segments are, but I would probably just leave it with the default setting. So you can see it's giving us a pretty close picture for what you have there. Now, if we had already solved the differential equation, then what we could do is go to y, and we could come down here and we could put our solution that we think, whatever we think it is, and then graph that and see if it overlays nicely on top of it. So I think we're going to see some of that in the next section. Okay, so this next example is not in your notes at all. So unless you need to print the new copy that I will try to send in an email to you guys. Now this type of example is very, very common on the AP test. So what they'll do typically is they'll give you a differential equation and then give you a bunch of slope fields, and you have to find which slope field corresponds to the given differential equation. Or it could go the other direction. They could give you just one slope field and a bunch of different differential equations, and you have to match that. So we're going to treat this as if it was 4 separate problems. So even though it is process of elimination, we're going to kind of ignore that on each one just to show what the reasoning would look like. Okay, so if I was given this differential equation, what's the first thing that I would notice? Well, I would try to think about what does it take for dy dx to be 0. I always start by thinking about that. If dy dx is 0, well, the only way that's true is if y plus 1 is 0. In other words, y has to equal -1. Now, why is this important? Well, if the derivative is 0, that means we're going to have a horizontal tangent. So we're looking for graphs that have horizontal tangents, and they should be horizontal tangents along y equal -1. So which one has that? Well, here's y equal -1. Those are not horizontal tangents. This one, not horizontal tangents. None of those are horizontal tangents, but this one, bingo. All of those are horizontal tangents. So that's the telltale sign for this one. That gives it away. This guy has to be 4. There are other things that we should notice in this picture as well. So what I typically do is analyze each of the quadrants. So I look at, let's say we look at the first quadrant here. In the first quadrant, x is positive and y is positive. Oops, I meant to put plus there. So if we go back to the differential equation, if both x and y are positive, well, there is no x here, so it doesn't matter, but so y is always positive, we're adding 1 to it, which means all of the slopes, all of the tangents should be positive slopes. And you can see All of them are positive here. If we go to the second quadrant, here x is negative, but y is positive. Now, the x being negative doesn't impact this differential equation because there is no x in the differential equation. So you can see all of these slopes, they're the same as these. Another way of seeing that is, if you look across horizontally on any row, all the slopes within one row are the exact same thing on all of these. And that's because there is no x in this differential equation at all. It's independent of the x. X does not change what the slope of the tangent is. Okay, so you could continue analyzing like that, going through each quadrant and trying to see, okay, does it make sense for it to always be positive or always be negative? We'll see more of that as we look at the next examples. So let's try the next one. Okay, so this one says dy dx equals y minus x. I would start the same way. Dy dx, when is it 0? Well, in order for it to be 0, 0 would have to be y minus x. In other words, y would have to equal x. So this is the line dividing the plane in half, so like this line right here. We're saying along that line, the slopes should always be 0. We should have horizontal tangents like this along that line. Well, this picture definitely does not have that, so it's out. So what about the next one? Well, this one starts off good. We have a horizontal tangent here, but quickly they're not horizontal, so this one's out. If we go to the next one, we can see this one indeed has what we're looking for. Along the line y equal x, each of these are horizontal tangents. So it definitely looks like that is going to work. Now there may be another graph that has that same thing, so you might need more information. So the next things you might look at is, well, let's look at the second quadrant again on this one. In the second quadrant, we know x should be negative and the y should be positive. If you go back to the differential equation, if x is negative, but we have a minus sign here, this is always going to represent a positive part, and then y is already positive. So the whole thing would have to be greater than 0 in the second quadrant. And you can see all of the slopes here are positive in that quadrant. Similarly, if we go down to the fourth quadrant, in the fourth quadrant we know that the x is positive, but the y is negative. So if we go back to the differential equation, if x is positive, well, this negative is going to mean we are subtracting something, but the y is also negative. So we have a negative here minus a positive, which means the whole thing is going to be negative. So all of these slopes in this quadrant should be negative. They should be pointing down, which we can see that they are. So those are some more things that you can analyze to help narrow it down. All right, let's try C. All right, C is basically the same thing as the last one, but we have plus instead of the minus. So I would start the same way, dy dx. When is it 0? Well, the only way it's 0 is if 0 is equal to y plus x. Subtract over, so y would equal negative x. Along this line, we should have 0 slopes. So that's going to be the line just going back the opposite direction. And if I draw that on this one, you can see all of those 0 slopes along that line. And I don't believe any of the other ones have that property. You could then go through and do the same analysis we did before, but you're going to reach the same conclusion. So for C, it's option 1. Okay, final one. So this is probably the one that's the hardest to see. Some of these can be very hard to analyze to actually see which one it has to be. Now we know by process of elimination that these are all out, so it's got to be this option. But imagine that we didn't have any of the previous problems, and you just had to do it by regular process of elimination. Well, we could try to do the same technique as before, but you'll see it doesn't work quite as well with this one. Start by setting that equal to 0, which would mean x squared plus y equals 0, which means x squared equals negative y. If I divided that over, we would have y would have to equal negative x squared. So along that curve, we would have to have horizontal tangents. Well, we know that the graph of that looks roughly like this. except my scale's probably off a little bit. And you just can't see it here. You can't see the horizontal tangents, but they are actually there. You can see one of them is here, another one is here, but the next one, when you plug in 2, you'd be all the way down here at 4. So they're just spread out too far to actually be able to see them. So that's not by itself is not going to give you a good way of being able to see which graph is actually correct. So this is where I would go through and analyze using each of the quadrants. So if we start with the first quadrant, x and y are both positive in this quadrant. And if we look at the expression back here, if you put positive numbers in each of these places, the overall expression should be positive. So we would expect positive slopes in that quadrant, and we can see that is true here. So let's actually rule some of the other ones out as we go here. This one would be out because this quadrant is messed up. We've got negative slopes in that quadrant, so that's how we would eliminate that one. All three of these, if you look at the first quadrant, they all are doing the right thing. They're all positive in that first quadrant. Okay, so we couldn't eliminate the other ones, but this guy's definitely out. If we go to the next quadrant, if we look at this one, then in this quadrant we have a negative x. Oops, keep doing that. So x coordinate is negative, y coordinate is positive. If you put a negative number in here, though, it's going to become positive, and then we're adding a positive to it. So the whole expression in that quadrant should be positive. The slope should be positive here, and you can see in this graph they are. In this one, they are not. We have negative slopes here, so that's how we would eliminate that one. So then this one, also all positive. So now we're down to just 2 and 4. And so the way to finish it out, you could do some analysis with these quadrants, but I would really look at this defining feature to rule it out as saying, well, we know that if you put -1 into the y value, you're not guaranteed to have a 0 slope because x could change that. So that's what would cancel this one out, and we would be down to this case here. So this is what we mean by analyzing the slope fields, looking at the different quadrants and different features in each quadrant to try to narrow down which differential equation is being represented by that slope field. Okay, next example. So it says the figure below shows the slope field for this differential equation, and then it says for what initial conditions at t equals 0 are the solutions constant. So we want to pick initial conditions, meaning along the y-axis. We want to pick ones that make it so the solutions are constant functions. Then we want to find out when would they be increasing functions, and then when would they be decreasing functions. So in other words, we want to know, let's do constant first. So we're trying to figure out what should y of 0 be so that we get a constant function. Well, constant functions have tangents that are horizontal. In other words, the derivatives would be 0. So what we're looking for is horizontal tangents. And we can see right here, starting right here, and it goes all the way across. That's a constant function. So if we take the initial condition of y of 0 equals 2, we will get a constant function. Okay, next one, if we look at increasing. Well, increasing functions should have slopes that are positive. So we're looking over here for tangents that go up. Well, we can see all of these over here, they're positive slopes. So if we pick any initial condition along this part, along here, we will have increasing solutions. For example, if I just pick a random one here, let's just pick this guy and then follow the tangents, we can see it's increasing. And all of them over here are increasing. So all we would need is we need y of 0 to be greater than 2. As long as we pick the initial condition to be greater than 2, these are going to increase. All right, and then decreasing. All of the values below 2 down through here, you can see all of these have negative slopes. And if we follow those, if we just pick one and draw out the solution, all of these are going to be decreasing solutions. Even the ones that are up here, it's decreasing really slowly, but they're all decreasing. So we would just need y of 0 to be less than 2 for those cases. And that's all they're asking for on that one. Okay, so the next type of slope field that we're going to graph is a special type. We're looking at specifically differential equations, dy dx, where the right-hand side is just a function of y. We've actually seen an example of this. If we go back to the very first one that we did, oh, sorry, this one was a function of x. Sorry, this is kind of the opposite. So this one is actually of the form dy dx equals f of x. So I'm saying, what if it's the opposite of that? Dy dx equals f of y. So as an example, it could be something like dy dx equals y squared minus 1. So just y's on that side. Now, what that means is, let's get back to it. Actually, I think, yeah, this was actually a perfect example of that. This is an example of what we were just talking about. So dy dt equals y minus 2. There's no t over here, right? Whatever's down here, the denominator of your derivative, it's not expressed on the right-hand side. And so what ends up happening is it means that the x-coordinate doesn't matter. So if you go along this, sorry, not horizontal. Yes, it is horizontal. As you go along the horizontal, along this row here, none of those slopes are different. They're all the same, right? You just pick an x value, or pick the starting y value, and then go all the way across. All those slopes are the same. On every single row, they are all the same. So that means to draw our slope field, we just need to get all of the slopes along the y-axis, and then we copy them all the way across. Whereas on that very first example, we got to copy them straight down, right? Everything in a column was the same. On these, everything in a row is the same. So that is all this is actually saying. So let's do one of these. Okay, so this says for what initial conditions do we get a constant increasing and decreasing? Same as last time, and then it tells us to sketch it. I would say let's sketch it first and then go back and figure out when we get increasing, decreasing, and constant. Okay, so notice in our differential equation there is no t over here, no x, no independent variable. So that means along each of these rows all the slopes are going to be the same. So we just need to figure out the first one, and then we can copy them all the way over. Now these do not come out nice, so when we sketch them in there, we are just going to approximate them. We're not going to make them exact. We really just care about positive and negative for the most part anyway. Okay, so first thing to notice that should be obvious, if we start with y equals 0, we're going to get horizontal tangents. So when you pick y equals 0, it wipes the whole thing out. So let's make this red. It's too hard to see here. So all of those are just going to be horizontal. Similarly, if y equals 2, they're all going to be horizontal. Derivative is 0 when y is 0 and when y is 2, just plugging into this. Okay, then let's do the value of 1. So when y is 1, you're going to get 1 here times 1 minus 2, which is a negative 1. So each of these are going to be roughly like this. Okay, I'm just trying to connect to get a slope of negative 1 there. Okay, then let's come down here and do this negative 1/2. So I'm just going to tell you, if you take negative 1/2 and plug it into this, you end up with 1.25 as the value. So that's supposed to represent our slope. That's pretty close to a slope of 1, so I'm just going to approximate it with slope of 1. Then plug in negative 1, you get a slope of 3. All right, 3 is pretty steep, so I'm trying to visualize connecting these 2 points here, and then just making it parallel all the way across. If you plug in negative 1.5, then you're going to get 5.25, so even steeper than this. And this is where we're totally fudging it here. Just make it steeper than the other ones and try to keep them the same all the way across. All right, come up to this row here. If we plug in 1/2, it turns out to be negative 3/4, which is kind of close to -1, so we're just going to approximate it with that. So it should be not quite as steep as this. It's just a bit more shallow than the one above it. If you plug in, what is that, 1.5, I think you end up with the same thing, negative 3/4. All right, and then go up another row, 1.25. If you plug in this value into the differential equation, you get a slope of 1.25. So it should be just a bit steeper than 1, tiny bit. And then plug in 3, you get out 3. So that's pretty steep. Okay, so that was just a pretty rough sketch of it, but it suffices. It gives you a decent picture of what's actually happening. So now let's go back and answer part A. To do that, though, let's look at a much more cleanly drawn picture. This has quite a few more segments in it. So if we were going to draw in just a couple of random solutions, I notice there are kind of 3 separate things that could happen. If we started, let's say, over here, if I took that as an initial condition, then my solution curve is going to do something like that. Anything above this horizontal line right here is going to increase like that. If we pick something in here, then it's going to do roughly something like that, approaching this horizontal line. And that would be true no matter where you pick in that range. And then down here, it's going to look something like that. So we can see our 3 different cases here. We've got our constant solutions at 0 and 2. We've got the increasing cases on above 2 and below 0. And then we have the decreasing case where our initial value is between 0 and 2. So let's write those out. Okay, so constant. For those 2 cases, we would need y of 0 to be 2 or y of 0 to be 0. That gives you the 2 horizontal lines. For increasing, there are 2 different ways we could get increasing. If y of 0 is greater than 2, that's this case here, we're increasing. If y of 0 is less than 0, down here, then we're also increasing in that case. All right, decreasing. Decreasing is on this interval right here, so that would be if your y of 0 is somewhere between greater than 0 but less than 2. All right, and that summarizes those 3 cases. Okay, this is our last slope field example before we do Euler's method. So this is an application problem. It says the logistic equation is commonly used to model populations with a stable equilibrium solution. That stable solution is oftentimes called the carrying capacity. The logistic equation is the solution to this differential equation. So this says the rate of change in p with respect to time is equal to 0.1 p times 1 minus p over 300. So these constants could be changed depending on the given application, the given thing that you're studying. So you could think of p as population in this case. So we're looking at what it says is the rate of change in population with respect to time is given by this. Okay, so we would want to start by sketching the slope field for this differential equation. Notice there is no t in this expression here. So it is just like the previous example, meaning that each row is going to be all the same slopes. So we really would just need to find the slopes along the y-axis and then copy them all the way across. So we're not going to do all of them, but let's point out a couple things that should be obvious. The first one is if you put 0 into this, it's going to wipe everything out. So you would get horizontal tangents along the x-axis, like the last example. But if you put p equal 300 in, this turns out to be a 1 then, and so this entire expression would be 0. So you will get horizontal tangents when the population is 300 as well. So each of these, whenever population is 300, your tangents are going to be horizontal. Okay, so then you would just need to go through and find the values at each of these nodes. So if you do that, if you actually plug them in, meaning plug 50 into this expression, what you get out is 4.2. If you plug in 100, you get 6.7. Plug in 150, you get 7.5. Plug in 200, you get 6.7. Plug in 150, you get 4.2. And these are all corresponding to slopes. And then up here, you would get a negative 5.8, I think, approximately. So you would then just need to try to approximate each of these slopes. So I'm going to save us doing that and just go to the graph. This is what it would look like. So this has actually extra nodes in it as well, more than the previous one. But you can see we have our horizontal tangents along the 300 and along the x-axis as well. So we've got tangent or slopes that are 0 along each of those lines. So now it's saying graph the corresponding solutions with these initial conditions. So we're actually doing 3 separate graphs here. If we start with the first one, if the initial population is 50, which would be here, we just want to try to follow the tangents the best that we can. It would do something like that. Next, if we did an initial population of 150 here, follow them again, and you can see what's happening is it's still leading us to this same solution. They're all becoming asymptotic to this 300, the carrying capacity. So we increase in this range up to that, and then we don't go beyond it. Okay, but what if the initial value was 350? Let's do that with, we'll do that with black, I guess. So 350 is here, and you can see that that actually takes us back down again to the same place. So all paths seem to lead to this 300. If you start anything above 0, it's going to eventually take you to the 300, and if you're above 300, it brings you back down. So how should we interpret this? Well, this tells us what the limit actually should be. Let's actually take that back to the other slide. Okay, so this says find and interpret that limit. So the limit is pretty obvious. No matter which path you take, as t goes to infinity, we seem to be going to this 300 no matter what. So then it says interpret what that means. Well, it's basically just writing out what we said. As long as you pick an initial population above 0 and below 300, the population will continue to increase until it reaches 300. If you, however, choose an initial population above 300, the population is going to decrease until it decreases down to the carrying capacity 300. Okay, in the final example, it says show that the solution curve is concave down for 150 less than p less than 300 when the population is between 150 and 300, and that it is concave up when the population is between 0 and 150 as well as greater than 300. So concavity, we remember, comes from second derivative. So we have to do the second derivative. So d squared p over dt squared. We're doing the derivative with respect to t of 0.1 p multiplied by 1 minus p over 300. Now notice we are taking a derivative with respect to t here, And that means that p is a function of t, so we're actually using implicit differentiation when we do this. You could differentiate right now, but you would have to use product rule. So I'm going to start by just distributing this term through the parentheses. So that gives me d dt of 0.1p minus 0.1p squared over 300. We could simplify this, but I'm going to factor that 0.1 out at the end anyway. So, oops, that's supposed to be a 300. So we'll do that at the end. All right, so now when we differentiate, the first one is going to be 0.1 p prime, because we are using implicit differentiation. The derivative of p with respect to t would be p prime, minus, the next one is going to be 0.1 times 2, bringing the exponent down, times p prime. Right, we're using implicit differentiation, so bring the power down, decrease the power by 1, leave the inside alone, and then multiply by the derivative of the inside. That's still over 300. Okay, both of these have a p prime, and they both have a 1/10 on them, so I'm going to pull that out. 0.1 p prime multiplied by 1 minus, and then I'm going to go ahead and cancel right here and here, put a 150 instead. So this will be p over 150. Okay. So the next thing we're going to look at is notice that the zeros of this are the second derivative of p equals 0 if and only if p prime equals 0 or 1 minus p over 150 equals 0, right? Either this term is 0 or that term is 0 for the second derivative to be 0. So we already know when this is true, right? This is true when p equals 0 or p is equal to 300. Right? That's what was given above in our slope field. The population, when the population is 300, the derivative was 0, and when the population is 0, the slopes of the tangents are 0. So that's where we're getting that. And then for this term here, if you solve that, you can see easily that that will be 0 when population is 150. So these are you could say, the critical numbers for the second derivative. So let's turn that into a sign chart. All right, and then I believe in the problem we didn't have to consider population being negative. Yeah, so this part here, if we partition this part is not necessary. But we do, make that dashed, we do want to look at the other subintervals. So what we're specifically looking at is we want to figure out what's the sign of population. Okay, so we're analyzing this expression here. So let's look at the three cases. Suppose that, let's just pick a test point just to make it easy. Let's pick 100. So if population is equal to 100, then p double prime, we want to know whether it's positive or negative. So let's come back up to the differential equation. When the population is 100, let's actually pull this graph down too so you can see it a little bit better. Okay, if population is 100, then notice all of these slopes are positive, which means the first derivative is positive. So the second derivative, that first part, it's going to be 0.1 multiplied by some positive number. I don't really care what it is, but it's a positive number, multiplied by 1 minus 100 over 150. Right, just plugging everything into that expression there. This is also going to be a positive number. So what we end up with is a positive times a positive. Right? Positive on the first part, positive on the second part. So it's positive, which means we are concave up there. All right, so we just do that again on the next interval. Let's pick a test point here, let's just say 200. So population is 200. All right, then second derivative. Notice, let's get the second derivative back down here. So p double prime was 0.1 p prime multiplied by 1 minus p over 150. Okay, so we're plugging into, think of it as two different pieces we're plugging into. So we need to plug in 200 to p prime. So here's 200, look at that slope. The slope is positive at that point. Hold on one second, let's move this to the background. Okay. Okay, so at 200, the slope there is positive all the way across, so p prime is positive, which means this first part is positive. Then plug into the second part, 1 minus 200 over 150. Well, this is going to be negative, so we've got positive times a negative. That's giving us negative, which is concave down then. Okay, and then the final one, pick some point out here. Let's just say 350. So if we come up here to 350, the p prime, the first part, this part here, is going to be negative because the slope here is negative. And then the second piece, 1 minus 350 over 150. Well, this fraction is bigger than 1, so that 1 minus that fraction is going to be negative. So we have negative times negative, which gives us a positive. So we're concave up there. So that establishes concave up between 0 and 150, concave down between 150 and 300, and then concave up again between 300 or from 300 on, which should match what they said back here. So we verified what they were asking us to verify. All right, we could write that out carefully in words, but I'll let you do that on your own. Okay, the last thing we want to cover in this section is Euler's method. Euler's method is a method for approximating the solution to a differential equation. It actually has a lot of similarities to Newton's method that we use to approximate the zeros to a solution. It uses an iterative process, so that part is really what's the same as Newton's method. So here's the basic idea. You have a differential equation, right? That is the same as writing dy dx equals some function of x and y, right? This is what we've been dealing with through this whole section. These are the types of differential equations that you could make a slope field for. You also have some initial condition. You plug in some initial x value, you get out some initial y value. So this is my initial point right here. Okay, so then the idea is the red is the actual solution to the differential equation. We do not actually have that. Okay, that would exist somewhere, but we don't know what it is. So we're trying to come up with a way to generate an approximation to this red curve right here. Okay, so to do that, what we do is we go to our initial point, go to this point here, and we form a really small, a really short tangent line at that point. So remember, tangent lines in general are written as y equals f prime of a times x minus a plus f of a. However, the notation in this particular example is going to be a bit different. So the derivative is actually f of xy. Notice it says that right there. The derivative is f of xy. And the a, well, this is actually the a. So the slope part is replaced by f of x sub 0, y sub 0, right? Because this f is actually referring to what the derivative is equal to. Then the x minus a would be x minus x naught, because a is the x naught. So that part's staying the same. And then the f of a is your starting y value. Well, the starting y value is just y naught. So this thing that you see here is actually the equation of this first tangent segment, right? That very first tangent line. And so the idea is you would want to make this incredibly short. Now we're going to continue that process on, meaning that at the we're going to pick a certain distance. We're going to call it delta x. we're going to travel along this green tangent segment for that, whatever that predefined delta x is, and at the endpoint of it, we're going to do the same process again. We're going to form a new tangent line and then go the same distance delta x again to its endpoint and just keep that process going. Now you can see that the blue is not following the red perfectly because there's an error at the very end here. This is off a little bit, and so then that error starts to compound. The amount that it's off the next time is even more. The amount that it's off the next time is greater. So it's not going to give you a perfect approximation to your curve, but the idea is if you make this delta x incredibly small, then the approximation should be pretty accurate. So let's actually see this in motion, see what it actually looks like. Okay, so here I have a simulation of Euler's method. We have a differential equation, kind of a nasty one, dy dx equals the quantity 3 minus y times cosine of x. And I have an initial condition of plug in 0, you get out 1. So what I did to get this first tangent segment that you see here is we plug in the coordinates, the 0 for x and the 1 for y, plug that all into this, and that gives us the slope of our first tangent. So then I formed that tangent line. And I decided I'm doing 10 approximations, 10 segments. So I took the interval, I'm just looking at the interval from 0 to 4. I divided it into 10 equal intervals, so my delta x is 0.4. So I went over 0.4 units and I stopped. This then gave me my first endpoint and my first approximation node, you could say. And then from that point, I took its coordinates. Whatever these coordinates are, I plug those back into this differential equation to get the slope of the next tangent segment. I then use that tangent segment, I go over again 0.4 units, I get a new endpoint, I then take that endpoint and plug it back into the differential equation to get the new slope, the slope of this line, and I just keep that process going. So this gives us a rough approximation of the solution. Let's actually see what the true solution looks like. So this is the actual solution curve to this differential equation, and you can see it's at least behaving in the same way, but it's not that close. So as with everything in calculus, if we want the approximation to improve, we should increase the number of little nodes. And you can see as I increase that, the approximation gets better and better and better. It's still always off, but it's off by less. So here's 100 segments squeezed into there. You can see it starts off really good, but then those errors continue to compound, and you can see they get worse and worse. But if we zoom in on that original part, that's pretty darn close. It's following the differential, the solution quite well. Okay, so let's figure out how do we actually get a formula for this iterative process. Okay, let's take a closer look at our tangent line formula. So remember, this equation here is equivalent to m times x minus a plus f of a. Right? This is just point slope form. This is our slope. Remember, our slope was given by the differential equation. Don't think of f here as being the equation of the solution. That is not true. It's just the equation that's part of our differential equation, the expression that generates the slope. So this is our slope, and then this is the point, x0, y0 is where it's starting. So that's giving us the equation for just that first segment. Okay, so now what we want to do is we need to get the equation for this piece here. So to do that, we need to figure out what is y1. That's really what we need to figure out, is what is the value of that point there. So y1 is found by plugging x1 into, right up into this, right? Plug it into that function, and that's what y1 is. Well, what is x1? x1 is simply x0 plus delta x. Right? x1 is the previous one plus our predefined delta x each time we're moving over delta x. So if I'm plugging in x1, I'm really just plugging in x0 or x0 plus delta x. All right, so if we take all of that and put it up into here, we get this. Right, just putting the x0 plus delta x in for x, and you can see these cancel, and you end up with just this expression. The slope multiplied by delta x plus y0. Now, if you do that process, this gave us the value for y1. If you go through the whole thing and do the same process for y2, you'll see that it has basically the exact same structure. So what is that structure? Notice that the subscripts in this expression are just one less than the subscript here. And the same thing is true in this case as well. So if we iterate that process, if I want the kth step, then it's just going to be f of x sub k minus 1, y of sub k minus 1, times delta x still, plus y sub k minus 1. So this gives us a formula to generate each of the y values that you see, each of these different y values. And then we can just connect them to draw the graph. All right, let's try one of these by hand. All right, so the example says, find an approximate solution to the initial value problem given by this differential equation with the initial value of y of 0 equals 1. And we're going to be doing this on the interval from 0 to 2. And we're going to use a step size of 0.2. And where this came from is we want to use 10 different segments. So if I took the width of that interval and did the whole b minus a over n like we did back with integration, you got 2 minus 0 over 10, which is where we're getting the 2/10 from. Okay, so we already know y0 is the initial value, which means it's that. y0 is 1. y1 in every single problem is going to be f of x sub 0, y sub 0, delta x plus y sub 0. So in this case, that is f of 0. X sub 0 is this, right? That's x0, that's y0. The y0 we said was 1. Then delta x we said is 0.2. And y naught is 1. Okay, that's just plugging in all the given information into that. And then you evaluate. So this, you plug 0 in for the x, 1 in for the y. So that's really negative 1/2. Right, just plugging in 0 and 1 into that expression, multiplied by 0.2 plus 1. And then you evaluate that. That comes out to 0.9. So we have our first y1. Technically, this corresponds to an ordered pair. The ordered pair would be, we're adding delta x to our original. So the x would be 0.2 because we started at 0. So the next x value would be 0.2 and the y value would be 0.9. All right, let's do the next one. So this one would be f of x sub 1, y sub 1, delta x plus y sub 1, which means it is f of the previous x, which would be 0.2, the previous y, which is 0.9, times 0.2 again, plus the previous y again, so 0.9. All right, if you evaluate that, you should get a slope, I believe, of, give me 1 second. Looks like negative 0.25. So again, this came from just plugging in the 0.2 and 0.9 into this expression. Then delta x, which is just still 0.2, plus the 0.9. Evaluating that gives you 0.85. So this is our second approximation point. The x now would be delta x plus this, so it would be at 0.4. We just keep adding delta x, and then the y value is 0.85. Okay, so you keep that process going, and you would need to do it 10 times. So you can see this is a big pain. So to make it easier, I did make a program for this as well. So hopefully, as long as you guys can get that calculus pack added to your calculator, let's show you how the program works. Okay, first thing we're going to want to do, notice if I go back to my graph, the slope field is still there. And if I tried to put something else in there, like 2 plus, let's say, I don't know, doesn't matter, it's going to graph right over top of that. This is staying there. And that's because this was added as a drawing. So to get rid of it, what you want to do, you can run the program again, which will get rid of it, or you can do second draw and clear draw. Now you can see that's gone. So let's clear both of these out. Okay, and go to Program, choose Euler, and starts off kind of the same way. It says enter a new derivative or use something typed into y1. So we're going to do new, and we're going to enter the expression that you see there. So you have x minus y divided by 2, alpha y divided by 2. One thing to notice, your fraction button, with the way this program is written, the fraction button will not behave the same way. If I try to enter a fraction in there, you don't see the normal fraction button. But notice it is bolded, and that means it will still kind of behave correctly as a long division bar, but I would probably stay away from using it and just stick with using parentheses where necessary. Okay, so that's our differential equation. X naught is the initial x value, which was 0 for us. The initial y value was 1, right? These are coming directly from this point here. And then delta x is 0.2. And then how many segments do we want? We wanted 10. And then it graphs it. It finds all of them for us, and it graphs them. And we can actually test them if you go to trace. This is the first point. This was what was given to us. If I use the arrow key, this should be our second point, which you see over here. Then third point, or that was technically our first. This is our second point, which we found there. Then third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So that would be our final point if they were asking for, you know, what is the approximation for the like what does they want to know what's y of 10 approximately, or sorry, not 10, in this case it was 2 was our final point. Y of 2 would be approximately equal to 1.743. So the program should make that quite a bit easier as long as you can get that onto your calculator. Okay, I believe that is the final example for this set of notes. This was a long one, very technical, so hopefully it made sense. If you're having trouble with the homework, obviously email me, and we'll see you in the next video.